the quantum capabilities and demonstration team at T.J. Watson Research Center. His research interests are focused on the coherence and control of superconducting qubits, multi-qubit device characterization, and applications of near-term quantum computers. Dr. Kandala received his bachelor's degree from IIT Bombay, and then he received PhD in physics. And after PhD, he joined the quantum computing group at IBM Research as a postdoc, where he explored the applicability of a noisy superconducting quantum processor to simulate small molecules and quantum magnets. And this work was recognized by MIT Tech Review as one of the top 10 breakthrough technology in 2018. And currently at IBM, he is building the tools for running large quantum circuits and exploring beyond classical quantum computation. So Dr. Kandala has many publications in many reputed journals like PRL and Nature. And recently, I think in this year, he published 2 Nature papers, which is quite impressive. So Dr. Kandala, I think you can share your screen and proceed.
Hi, am I audible?
Yes, you are.
Okay, wonderful. Thank you.
Screen is visible. Screen is visible. Just click it full screen. Yes,
Yeah.
good.
Okay, wonderful. So, how are we doing questions? Should I try and keep a look on the chat, or will someone interrupt me if there are any questions?
Yeah, if participants have any questions, he can interrupt you. And in the meantime, I will look into the chat box and I will ask the question.
Okay.
And just let you know that the talk is divided into 2 parts. 45 minutes are for talk and 15 minutes for discussion.
Okay. Thank you. Lovely. Thank you so much for the invitation to present here. It's 6 a.m. in the morning here in California, where I currently am at. But I really want to contribute to this, particularly to the ICER family, which is something that's very close to my heart. So this is the work I'll be talking about. Before I just dive into this, I just wanted to start off with a bit of a personal acknowledgement. Just honor my my late father, Professor K.V.R. Chari. In addition to a vast legacy of NMR research in India and scientists, his really selfless and inspiring dedication towards institution building over the last 15 years, which led to not just one institution, but 2 academic institutions of very high repute. This journey I find deeply inspiring, and you can read more at this link. But yeah, this is dedicated to him. Okay, and so today I'll be talking about a very recent paper that came out yesterday and was featured on the cover of Nature. The title is Evidence for the Utility of Quantum Computing Before Fault Tolerance. It's a title that we debated upon quite a bit internally within the team, and I think I'm pretty convinced that this is something we can justify, and I hope you'll walk through this with us. It's quite the journey. Perhaps the culmination of about 6 to 7 years of ideas in quantum error mitigation maturing and going hand in glove with the hardware progress that we've made at IBM. And so before we even dive in, I really want to thank the people who did the work um, the, on the IBM, and Young-Suk Kim and Andrew Edens really did all of the heavy lifting to get this project through. The work on error mitigation over the last several years has been a long collaboration that I've really enjoyed driving with Kristen Teme and Sergey and Jay Gambetta. We also had the opportunity to collaborate with a brilliant graduate student, Sujant Anand, and Mike Zalotel's group at the University of California, Berkeley, whom we relied for classical simulations. And then, as you will see, I already mentioned this at the start, as you'll see, the work is very, or the experiment I'll be talking about is extremely crucially dependent on the kind of devices we've been able to build, and these kinds of devices, building them go well beyond this limited author list. And I really have to acknowledge the contributions of the entire IBM quantum team that really made this experiment, the systems and the supporting infrastructure possible. And you'll see why this is all a very crucial part of the experiment. Okay, so I think before we go ahead, maybe it's important to state the obvious. We're not claiming that advanced algorithms such as Shor's factoring can be done without fault tolerance. What we're instead saying is that if you look at the vast majority of near-term quantum algorithms, what are things that people are trying to run? All of these depend on running a short depth quantum circuit, a circuit that you can fit into your coherence budget, and then they rely on the measurement of expectation values at the end of the circuit. Okay, and basically these expectation values, even though the circuits are short depth, are corrupted by noise. And what we're showing here is that even with the quantum computer that exists today, there is a way to access reliable expectation values at a scale that's well beyond brute force classical computation, and where leading classical approximations break down. This, we're arguing, is evidence for the utility of quantum computing even before we have full error correction, fault tolerance. Right. So I think this one slide for me encapsulates why building a quantum computer is incredibly hard. Right. If we look at the basic building blocks of our regular classical computers and compare them with the basic building blocks for our quantum computers and look at the error rates, we're looking at 23 or 24 orders of magnitude in difference in error rates. Okay, and this has been known. This has been known to be a challenge for many decades already, right? And the well-known theoretical solution to all of this has been some form of quantum error correction, and this will be necessary to access all the things we want to tap with quantum computing. And the basic idea with quantum error correction is you want to encode your quantum information in a larger lattice of qubits. You want to delocalize your quantum information, and then when you have local errors, those don't corrupt the information as quickly, so you have the opportunity to detect them and correct them and so on. Okay, so this has been one motivation to build large lattices of qubits. At IBM, our qubits are based on superconducting quantum circuits. You can think of these as basically LC oscillators, but with some nonlinear inductance. That leads to basically an anharmonic LC oscillator, which means that you don't have equally spaced energy levels, but you have some differences. The 0-1 transition, the lowest two levels, have a unique transition frequency compared to the rest of the levels in the circuit. And these levels, the 0 and 1 levels, you can use as your computational basis. Okay, and you want these levels to be sufficiently unique compared to other transitions, and all of this you can really engineer. I mean, you essentially have access to a man-made artificial atom here. You can really engineer these by circuit parameters, and for instance, for typical parameters that we work with, your 0-1 transition, is the next nearest transition is about 5% away from what the primary transition is. Okay, so these are the basic building blocks. Josephson junction-based circuits, typically with this kind of large shunt capacitance, and these are called transmons. Okay, and once you have these transmons, if you want to look at what a simple 2-qubit circuit is, and this is really the basis for many of the large processors we've been building, you have one transmon here, you have a second transmon here, and then you have some resonators for driving control pulses to the qubit, and for measuring the state of the qubit as well. This control can happen with just microwave pulses. I didn't mention it, but I indicated on the last slide that 0-1 transition is about 5 gigahertz. So with fairly off-the-shelf microwave electronics, you can control and manipulate the state of your qubits. It's also important to have the ability to drive entangling gates to entangle pairs of qubits, and for that you also need to have a resonator that introduces some form of coupling. And this is the coupling resonator, and with because you have this kind of coupling, also with microwave pulses, you can drive 2-qubit entangling gates. I won't get into those details today, but those are based off a gate referred to as cross resonance. Okay, so this has been the basis for building larger and larger lattices of qubits. One motivation for building these devices is, as I said, trying to delocalize your quantum information for error correction. So we've gone up to now 433 qubits, but even at this scale, we're not quite at a place where one can do practical error correction. We're not quite at the scale where you can do you can have fault tolerance. That will require a much larger set of qubits. Okay, but we have these devices, and if you look at even the 65-qubit processor, one could argue that at this size, you're perhaps already beyond what one can do by brute force classical computation. What one can do by just multiplying out matrices. That requires an incredibly large amount of memory. That's something you probably already can't do. So one can ask the question then, well, you have these large numbers of qubits, but you don't yet have fault tolerance. Is there something you can do in the meantime? Okay, and so let's do a very simple calculation, a back of the envelope calculation. Let's assume that I had about 100 qubits, and you can imagine that I wanted to run a circuit with about 10,000 2-qubit gates. Okay, perhaps the state of the art for 2-qubit entangling gate fidelity is about 99.9%. And if you ask the question, what would be the fidelity of the state, which is a measure of accuracy or measure of the overlap of the state you have with the ideal state, at the end of a circuit like this, it's an incredibly small number. It's just 5e minus 4, right? So the question is, what can you do if your state fidelities are so poor, right? Then one could ask the question, well, perhaps the business of preserving the quantum state, so preserving the state fidelity, which is what we want to do with quantum error correction, can be separated from the idea of trying to estimate certain properties of the ideal state. Maybe that's one question we could ask. And here again, it's quite useful to think of a very simple example. Let's assume that we had about 1,000 spins, okay? And all of these are aligned in the same direction. And so we have a net magnetization of about 1, and assume that we flipped one of these spins. Okay. Now, if you looked at the overlap of these two states, which is going to give you a measure of fidelity, that's going to be 0. Okay. You basically have 0 fidelity. Instead, if I asked, well, what's the magnetization? What's the global magnetization of this entire chain? That has only been affected in the third digit, right? If I asked what is the magnetization of the particular spin that flipped, that's going to be completely wrong once again. But if I asked what is the global magnetization, that's not too bad. So perhaps fidelity should be seen as more of a worst case metric. Okay? And perhaps there are other quantities that we can still benefit from, that we can actually measure fairly accurately, even with noise. Right? So quantities like this global magnetization, observables, properties of these quantum states, are these interesting things to measure? Are these expectation values that we refer to as, are these interesting things to measure? Turns out, yes, this is exactly what the vast majority of near-term quantum algorithms rely on. These could be, just like the example we discussed right now, going even beyond product states for more complex interacting spin systems. You might be interested in things like magnetization, correlation functions. If you're trying to run algorithms in quantum machine learning, these are relevant for kernel estimation algorithms. If you're trying to solve variational quantum eigensolvers for molecular simulation and estimating binding energies, it also reduces to the task of measuring an expectation value after a short depth quantum circuit. So these are relevant things to do. Okay. So this is a path we went down, even in 2017. This is exactly what we wanted to do. This was an example of the 7-qubit processor that we used back then, but the experiment here was really run on 4 qubits with a depth 2 circuit. And what I mean by depth is the number of parallel 2-qubit entangling gate layers. And so with this kind of a circuit, we were trying to solve for what the energies would be as a function of interatomic distance for the small molecule lithium hydride. It's really a toy problem. Okay, but we're trying to address this with a different paradigm of computing. You want to understand how does something like this perform on a quantum computer. So because it's only 4 qubits, you already know a priori what the correct answer should be. This you can solve exactly, and you know that this is the expected trace. And once you run this experiment on a quantum computer, those are the energies that you get, right? And you already see these very big deviations, which are in part or largely actually due to noise. Okay, so if you took data like this and showed this to a quantum chemist and asked them if this is something that they could make use of, the answer would be a resounding no. These kinds of accuracies are nowhere close to what's relevant practically for quantum chemists. Okay, so is there really any hope then to do something even with this business of measuring expectation values, right? So about the same time, what my colleagues at IBM, Kristen, Sergey, and Jay, and also simultaneously Simon Benjamin's group at Oxford, essentially invented are techniques known as error mitigation. Techniques where but even with using a noisy quantum computer, by running many different noisy quantum circuits, you can reconstruct expectation values that could be noise-free or have a reduced noise-induced bias. Okay. And I'm basically going to talk about one of these techniques. This is called zero noise extrapolation, where if you had some expectation value that you're interested in, you can express that as a Taylor series in lambda, where lambda is some noise parameter. And the idea is you want to suppress these higher order noise terms, and you want access to this E star, which is basically the zero noise limit. Okay, that's the basic goal. Okay, so assume that me as an experimental physicist, I have very, very precise control over the noise. Okay, somehow I can do something to my dilution refrigerator and precisely amplify the noise in a way that I care about. So this would have been the measurement at the base noise level. And then I want to amplify the noise by a factor of C. Okay? And I've remeasured this, and I've only written this down to the leading order term being order lambda squared. Right? Now, by combining these two estimations, I can construct a new, by combining these two measurements, I can construct a new estimate where now I have suppressed the leading order noise term to order lambda squared. Okay, and this is a very simple piece of math where you see that you can essentially cancel this term. In principle, this doesn't need to be only with two measurements. You can go up to n measurements and further reduce the estimate to order lambda to the n. Okay, at some point you'll be limited by sampling error. Okay, but in principle this can be done. The question is, well, how do you actually measure these expectation values of this amplified noise rate? That's not something that's trivial to do in an experiment. Okay, so the one thing we did was basically we went down this path of using a trick called pulse stretching. So the idea is that if under the assumption that your noise is time invariant, then you can essentially try and rerun the circuit with control operations that are all stretched in time. So if the noise is constant, you can imagine that, okay, if my 100 nanosecond gate, I stretched it out to 200 nanoseconds, that would effectively, if I reran the circuit, that would effectively amplify the noise rate by a factor of 2. Okay, and these are assumptions that we have to consider very carefully the validity of. But this is something one can do, right? So you have some measurement at a base noise level, and then you amplify that noise, and you have a measurement at an amplified noise level, and then by using these two measurements, you can extrapolate to what the expectation value would have been in the absence of noise. Okay, so with this basic idea, we revisited 2 years later the lithium hydride experiment that we originally had, right? So this was the first experiment, and then the same experiment the second time. You can see that these are basically the energy estimations at different noise levels. They're still fairly off from the right answer, but by combining these, you can extrapolate to what the results should have been in the absence of noise. And now these green dots basically fall a lot more on a lot closer to the ideal the ideal curve. Okay, so this was very promising. This was quite exciting, but it's still only 4 qubits. Were there any questions at this point that were worth addressing? I can keep going ahead. Okay, wonderful. Something? Okay, right. So the question is, well, how do you go? Yeah.
I have a question in the chat.
Okay. It's not something I have access to because I'm sharing my screen. Would someone mind reading?
I was just wondering, how is this green curve obtained?
Oh, the green curve. So this is just a 4-qubit Hamiltonian that you have. So you can do this by just exact diagonalization. So you can express, you can express the Hamiltonian in a matrix form, and then you can diagonalize to have access to what the energies are. But this is something you can do because it's only a 4-qubit Hamiltonian. This is not something you might be able to do, with exact diagonalization if you had a much larger Hamiltonian. But it's a great question. Thanks.
Thank you.
Okay. Yeah, please feel free to interrupt. I don't quite have access to the chat right now, so because I'm sharing my screen, but yeah, I'm more than happy to be interrupted and try and address questions. Okay. So how does this scale? So if you look at the remain determined at Taylor series, it's going to have something of this form: the number of qubits, your lambda noise parameter, which loosely you can assume it to be like the inverse of your coherence time, and then capital T is your total evolution time. Okay, this is going to be your remainder, and essentially for this extrapolation to make sense, you need this number to be small. Okay, so what is this telling me? That if I want to scale my experiment, either in number of qubits or the total circuit depth, which will affect the total evolution time, I also need to scale down my noise by a similar factor to keep this relatively small. That is a very challenging task. And if these bounds were indeed true, it probably would be very hard to scale this experiment up. But this was something we basically tried to test out in this work that we recently had published in Nature Physics, and this really laid out some key insights for how we could scale zero noise extrapolation as a method to sizes beyond perhaps what we can do with brute force classical computation. Okay. And then the circuits there were, we went up to 26 qubit circuits with a depth of 120. So in addition to zero noise extrapolation, we've also worked a bit on techniques referred to as probabilistic error cancellation. This is the basic lay of the land. You might have heard a little bit about our intent to try and get to this land of 100 by the circuits of this volume and try and provide accurate measurements. And basically the experiment I'll be talking about today then is going to be an experiment with 127 qubits with a circuit depth of 60. Okay, and this is very, very different from, it's at a completely different scale from the 4-qubit experiment I showed. So what's changed over the years? What's really made this current experiment possible, right? One is building a 127 qubit quantum computer, and all of the supporting infrastructure and the software that goes with trying to build a system of this size. So over the years, we've systematically increased the scale of our processors, and now they're pretty complex. We have these Eagle devices with 127 qubits, even 433. But just building large scale computers isn't enough. You also need to have quality of operations. So for that, you need your qubits to have very good coherence times. You need to preserve your quantum information as much, as long as you can. It directly connects to, for instance, the kind of circuit depth you can run. If you had more coherence, you can have more layers of gates and not lose information as quickly. And so that's very important. And so if we looked at the first revision of the Eagle processor, which I'm going to call R1, and compare it to the rev that we used in the experiment, rev 3, we were able to achieve about a 2 to 3x improvement in these T1 times. And the median T1 times were close to about 300 microseconds, which is pretty incredible for a quantum processor with transmons at this scale. The other aspect is actually calibrating a device that's this large. How do you get all these links to work, and how do you optimize for their performance, their fidelities? So typically in the past, we used to optimize every 2-qubit gate link, individually, trying to maximize its gate speed. For the circuits I'll be showing you today, you'll see that they're very ordered circuits, which have a lot of parallelization, because of the max 3-way connectivity here. You can basically consider every link to be parallelizable. So all the blue gates can be run in parallel, or the red can be try and optimize for the performance of the entire layer, right? So there were innovations that we came up with there to further optimize this kind of performance, and even with that, we were able to improve the fidelities of 2-qubit gates and the performance of the entire layer. Okay, the other crucial part is improving the noise manipulation, right? How do you amplify the noise in a very controllable fashion? And this connects to for instance, the ability to manipulate this noise in a controllable way is then going to affect the accuracy of how well you can extrapolate, what kind of extrapolations can we attempt. So really going beyond this pulse stretching that was something we were doing in the initial Z&E experiments. There were very important advances here. Okay, so I'm going to refer to the techniques we used for zero noise extrapolation as probabilistic error amplification, and I'm going to talk you through a simple example of how is it that you're able to amplify the error in this probabilistic fashion. Okay, so let's consider this very simple 1-qubit example. And we basically want to measure some observable A after the application of some noisy unitary on this initial state. And this measurement is basically going to give us access to this noisy expectation value at a base noise level. Okay, and one thing we can do is this noisy unitary, we can model this as some noise channel that acts upon the ideal unitary. And now let's say that we want to remeasure A, but now at an amplified noise rate, and perhaps this could be a gain factor of 2. Okay, so looking at how we model that circuit, that would basically, you could say, I'm going to add another noise channel here to act upon the previous circuit, and this would, if I measured the expectation value, this would give me access to the noise, to the expectation at this amplified noise rate. Okay, but this isn't something you can do in practice. Okay, so how does one then implement something like this in practice? Let's maybe assume that we had access to what this noise channel was. For simplicity, let's consider this to be a simple poly channel with some bit flip error rate given by little p, and basically in this equation, and by linearity, you can basically see that you have now 2 terms in that expansion, which basically amount to probabilistically sampling between 2 different circuits. So you had your original circuit with this U tilde, which was the noisy gate, and now you're inserting either an I or an X with either probability P or 1 minus P. Okay, so if you had access to these probabilities, the error probabilities for the noise channel, if you were able to characterize that noise channel, then by probabilistically sampling over different circuits, you're able to access now the expectation value at an amplified noise rate. I know that I considered a very simple toy example with a very simplistic with a very simplistic noise model, but in principle, you can have a more complex noise model here, and the safe math follows through. We also considered a very simple gain factor of 2, but in principle, you have great control over. You have essentially arbitrary control over what you want that gain to be, and that will simply change the probabilities with which you sample these different circuit instances. Okay, so you can also make this go negative. You can make this gain go to -1, and then you effectively cancel the noise, and that's referred to as probabilistic error cancellation. But that comes with an additional sampling overhead that I won't get into. Okay, so this was a very simple 1-qubit example, but that's not what we are working with in practice, right? We have much larger circuits, and these circuits, perhaps we can construct these as layers of noisy 2-qubit gates. So this layer includes many parallelized 2-qubit gates, which are all noisy, and we can consider these to be interleaved with single qubit operations. And once again, let's model this this noisy gate layer as some noise channel acting on this noiseless unitary. Okay. Now for this larger circuit, the noise channel will have a lot of contributions. You can have crosstalk errors. These can be classical crosstalk from microwave signals. This can be quantum crosstalk from unwanted couplings. You have your decoherence, your T1, T2 loss, interactions with defect systems in these Josephson junction devices that also lead to decoherence. You can have correlated errors. You can have control errors. Perhaps your gates aren't perfectly calibrated. Certain fluctuations in your control electronics that cause some errors. There are a whole bunch of errors that could actually be going on, and all of these need to be captured in this noise model. Okay, and this is a very, very complicated challenge because this in general requires the knowledge of 4 to the n by 4 to the n parameters. Okay, so we have to simplify it, and this is a polytransfer matrix representation of that noise model. You have basically these 4 to the n by 4 to the n terms, and the one trick one could do is to twirl over the noise channel. And what that means is for every qubit you insert you randomly sample a polygate, and on the other side of the layer you basically have an undoing poly operation, so that this is now logically equivalent to what the layer was originally. There is no difference. But then if you average over many different poly randomizations, you can basically simplify this arbitrary noise channel and tailor it into a poly channel, a channel that's diagonal on the poly basis. And now you only have these diagonal terms. Okay, and this is something you have to access to on average. This is over many different poly randomizations. Okay, but this is still not quite straightforward, because even in this diagonal form, you're still dealing with 4 to the n with 4 to the n terms, right? 4 to the n minus 1 terms. So for this, you really have to rely on some physics, and the essential part of being able to achieve some form of noise characterization is to reduce this exponential complexity in learning and characterizing the noise channel to something that's polynomial, right? And for that, we have to make some assumptions about the locality and sparsity of the noise. And for this, we introduce what's called the sparse poly-Limblad model, which was introduced in this paper. And basically, here the composite noise channel can be constructed as a product, as a composition of more simple poly maps. And because we make an assumption about the locality of the noise, basically we're only going to consider those poly error terms which are going to be single qubit terms for every qubit, and then and weight 2 terms for every connected pair of qubits, right? And what this means is, for this kind of architecture, this heavy hex architecture with maximum 3-way connections, this means that you basically are going to end up with only a linear number of error terms that you need to consider, and associated with those a linear set of probabilities, right? And basically the task, a linear number of these error probabilities or model parameters. And this basically, this form is very closely represents what I had on when I was introducing probabilistic error amplification for the 1 qubit scenario. The task reduces to having some estimate of these WIs for an arbitrary noise channel. Okay. So how do we even learn this now, right? So in general, if you had a poly channel, you basically want to learn these fidelities, which are basically the eigenvalues for this. And the typical approach here is if you basically amplified this error by repeating these noise channel multiple times, measuring in different bases, and measured some decay in expectation value as a function of depth, then you have access to these fidelities by just a fit to the decay, and this has been studied by Flamia Wallman and other papers. But the challenge here is you can't only amplify the noise channel. The noise channel is connected to the gate, and so what you can then repeat are the gate layers. So assume that the gate layer was a layer of C naughts. You can make an identity equivalent block with 2 C naught layers, and then repeat this block multiple times, measure in different bases, look at the decay, and then fit to that decay. Because of these gate layers, your fidelities will get mixed, and you end up with products of fidelities instead of just one in certain cases. And then one can ask, well, how many of these fidelities we need to estimate? Because of this sparsity or this locality assumption that we made about the noise, you basically can get away with you only have a linear number of model parameters to learn, so you can get away with a much smaller number of these fidelity estimations, from which you can then estimate your model parameters, okay, by a nonlinear least square optimization. And the details of that I'm skimming over, but you can look at the paper on the sparse polynomial model I cited a couple slides ago. Okay, so with this essential scheme, you can now learn the noise and obtain an average noise model for essentially a 127 qubit gate layer. Okay, and here basically this kind of model captures, as I said, individual terms on every qubit, and then you have 9 weight 2 error terms for every link that connects a pair of qubits, right? And the crucial element here is basically we've reduced the learning complexity from something exponential to something polynomial. So we've reduced that from having to learn about, this amounts to like 10 to the 76 something parameters, to just a little over 1,000. Okay. One natural question one can ask is, well, this kind of noise model, is it very representative? Does it represent the device? You can run a few simple sanity checks. You can look at qubits which have poor coherence times. This could be because of interactions with defect systems, and those will typically pop up in this plot, as elevated error rates, and so that is a useful consistency check. But there are also other things one could do. Okay, with that, once you have access to the noise model, then very similar to how I described in the 1 qubit example, you basically, for every gate layer, you introduce these poly randomizations, and you're inserting these poly gates by sampling them from a distribution that is based on the learned noise model, and then on average, you're going to have access to what that expectation value would have been at this amplified noise rate. Okay, so this is an example of an experiment in practice. We can run this experiment over about 2,000 instances, and G equals to 1 is the base noise level. The 1.2 and the 1.6 happen at this elevated noise levels, and then you can see you take about 2,000 different circuit instances to converge to what that amplified noise measurement is. Once you have these different expectation values at these different noise levels, you can extrapolate to what the zero noise limit is. You can do a linear extrapolation. In this case, the ideal answer was supposed to be 1. I haven't given you details of what the circuit was or any of that, but that's what it was supposed to be. So you still have some bias because you only suppressed up to second order terms in the Taylor series. But then you can also try more interesting extrapolation, such as exponential extrapolation, which was introduced by Simon Benjamin's group. Okay, and that seems to work a lot better. So we have a device, we have a very promising technique to manipulate the noise in a very controllable way. And then what was the experiment that we primarily ran? Can I take about 10 minutes? Is that good?
Yeah. Okay.
Yeah. Any questions worth addressing at this point before I dive into the meat of these things?
There is a question in chat box by Narendra Hegde. So Narendra, are you here? You can ask directly.
Oh, yeah. Hi, Abhinav.
Yeah, please. Yeah, please.
Yeah, my question is regarding how this, when you perform this error mitigation, you have an extra overhead, how this scales. Whether is this overhead is in the number of shots?
Right. So this, I mean, so in principle, I'm having to run 2,000 unique circuits, right? So so there is an overhead in terms of number of circuits, number of shots. Maybe if I can quickly go back. Yeah, if you want to just look at this, one way to visualize it is the number of shots that you take for a measurement for every noise level. That's going to give you some error bar, some sampling from sampling, and then you're going to try and extrapolate with these error bars, and then you can imagine that variance is going to further increase on your extrapolated estimate. So to suppress this down, you need more samples here and here to reduce the size. But specific to this probabilistic way, yeah, it also comes across as running many different circuit instances as well to effectively get the expectation values to converge to these levels, right? I mean, so if you just stopped here, clearly you wouldn't have gotten access to the right amplification estimate, right? So you needed to run a few thousand to get things to converge.
So it is like a constant overhead, you say?
So it depends on the noise rates.
I see.
And it also depends on the details of the technique. That's also another aspect. So if I haven't spoken about the probabilistic error cancellation, but there in particular, it's very easy to quantify what that overhead is. And it's something that can be exponential in the number of qubits in your circuit depth. But the game there is basically that if you can suppress your noise rate sufficiently, then that exponential doesn't blow up. That's the basic idea of the overheads for basically all of these techniques.
I see. And the other question is, when you have errors like depolarizing noise channel, these errors can propagate through your circuit based on some casual light cone. So you made some assumption that like sparsity assumption and locality assumption. So is this valid or for this type of noise channel also?
Yeah, absolutely. Because you're basically, I mean, so I'm giving you an example of just one noise channel here, but essentially you have blocks like this for every layer. So you're essentially mitigating on every layer in some sense almost, or you're amplifying the noise in every layer. And so yes, in general, you have errors propagate through the circuit and all of that, but then within this single gate layer, that's where you're manipulating the noise. Okay, so that extends to even when you go to the full circuit. So to be even clearer, right? So you have all of these different layers, right? And for every noise channel, you're learning the noise channel, and then you're manipulating the noise there.
Okay, that means the error is kind of not propagating. You are immediately fixing the error at each layer. Okay, thanks.
Fixing or amplifying, yes, exactly. Right. Okay. Yeah, thanks for those questions. Okay, so what was the experiment we were trying to do? So we're trying to run a very poorly trotterized time evolution of a 2D transverse field Ising model And this is basically, we're going to look at a spin lattice that shares the hardware topology. The ZZ is basically the Ising interactions between nearest neighbor spins. This is the transverse field. We're basically going to start the evolution in some initial state, and then once we quickly turn on an interaction, we're trying to study what the evolution of this spin system is. For the experiments you'll see here, we're going to fix the circuit depth. We're going to fix the number of entangling gate layers, and then measure expectation values at the end. And then we'll do that as we sweep some parameter. In this case, it will be this transverse field. Okay, and here basically every layer is going to be composed of these single qubit rotations, Rx theta gates on every qubit, which are going to try and implement this term in the Hamiltonian evolution. And then for all the ZZ interactions, you're going to essentially apply ZZ gates on every link in the device, because, as I mentioned before, because of the connectivity of this device, you can implement this in three steps. And there's going to be a red layer where all these the red links are driven in parallel. There's going to be an associated noise model with that we learn, and we manipulate the noise in that first layer. Similarly for the blue, similarly for the green, okay, and so on. Why do I call this poorly trotterized? Because we're going to trotterize these to a form where these theta j's, the trotter steps for the ZZ angles are fairly large. This is going to be pi over 2. And this is for simplicity, basically, because this gate we can then implement using just one C0, which is what we have in our natural gate set for the device. So once you fix the ZZ gates to pi over 2, you basically have access to what's called as a Clifford circuit, and I'll explain why this is important in a bit. But for the experts, you now have access to the Clifford circuit when these single qubit rotations are either 0 or pi over 2. Okay, so what have we basically done? Like, just to get some sense of visually how large these circuits are, particularly compared to the 2017 circuits. This is now the volume of 127 qubits with 20 gate layers. Just to give you some visual sense of the progress we've made to enable experiments like this. Okay, so at 127 qubits depth 60, in general, you are beyond brute force classical computation. You can't do a matrix multiplication of a massive 2 to the 127 by 2 to the 127 matrix and estimate expectation values. We don't have that kind of memory. This is just computationally unfeasible, right? So how do you, if your circuit volumes are that scale, how do you even build confidence? How do you even know that what you're doing is correct? Okay, this is really the key first step in being able to run circuits that you can verify. And these families of circuits called Clifford circuits are very, very interesting because you can run very complex entangling circuits, prepare complex entangling states, and still you will have access exactly to what certain properties of these states are. And these are extremely valuable to first build confidence in the device. Okay, so as I said before, the angles that are relevant for that in this theta sweep are 0 and pi over 2. If we look at the global magnetization, the magnetization of all 127 spins, you measure the raw data for the magnetization. That's going to be in green, and the ideal answer was supposed to be 1, and you see some bias from there, but then by this exponential extrapolation, you're able to get access to a much better estimate for what the global magnetization is, much closer to the correct answer. And similarly, at pi over 2, the magnetization should have been 0, and that's where we end up, right? So at these 2 points, we seem to be getting the correct answer. Okay, we can verify. So this is good. This is something that gives us some confidence. And now we can basically ask, let me look at these non-Clifford angles, which might not be verifiable, right? And I have, because of the form of the circuit, I have a very nice way of doing that. I can simply sweep between 0 and pi over 2. And once again, you look at what the devolution is. The green represents the unmitigated at the base noise level, and then you can amplify the noise, and now you get the blue. Okay. Well, what's correct now? How do you know what the right answer is, right? And for this, we really had to approach a leading group at the University of California, Berkeley, Mike Zaletel's group that really specializes in classical simulation techniques for quantum circuits. And so basically the idea is now, because you can't do brute force classical computation, you have to rely on what are called tensor network methods, basically methods that approximate your quantum wave function. Okay, and you have to think of this as having some approximation parameter that we're going to call the bond dimension, and you can basically try and interpolate between these two extremes. One where the bond dimension is 1, and you just have product states which are completely just basically like classical, and then with exponentially large bond dimension, you have an exact representation of the wave function. Okay, and you're going to try and interpolate between these two, and where you land will depend on aspects like the amount of memory that you can use in your classical supercomputer, or the runtime that you're willing to invest in your classical supercomputer. Okay, so this is something we can do, and there are two different tensor network methods that were attempted. One very similar to what I showed, it's called matrix product states. isoTNS is a 2D extension of that. And basically when you run these, what you end up seeing is that, you know, at the start of the evolution, for small theta angles, when entanglement isn't as large, you can see pretty good agreement with the experimental data. But then as you go to larger angles, there is this deviation. Okay? So how do you now know what is correct? Right? So this was a big question for us. And then what we figured out was, okay, we're actually looking at a fairly low weight observable. This is just the magnetization. This is well averaged over all of the single site magnetizations, but for then each of those, it's a low weight observable, and the depth is fairly small. It's only a depth of 15. So if you try and draw out what's called the light cone, basically if you try and ask what are all the qubits that play a role in the estimation of that single site magnetization, then even though the entire circuit that was run was 127 qubits, it's only a small number of qubits that actually play a role in the estimation of that observable. So in the classical simulation, you can basically get away with you can just get rid of all of these other qubits, all of these other gates, simplify that circuit a lot for every single site, and now you have access to a smaller number of qubits that you can once again do brute force estimations with. And now, but by doing this, if you look at what the exact result is, that falls bang on top. It's excellent agreement between the experiment and the exact evolution. Okay, so this was really promising. So we know that at these larger angles, the experiment was producing more accurate results than these methods that we considered here. Okay, right. Now we want to increase the complexity of what we're trying to do. So if this pi over 2 point actually is the more interesting point, it's the one where you have more complex entangling dynamics. One question one could ask, well, is okay, you can either interpret the magnetization going to 0 at pi over 2 as your extrapolation and error mitigation working perfectly, or you can also interpret this as you have a maximally mixed state because everything is depolarized by that point. And so how do you know that your state was not completely noisy, right? So to address that, what you want to do then is you want to measure an observable that's a stabilizer at pi over 2 that ideally takes the value plus or minus 1, and this you can verify by Clifford simulation. So we pick one such observable. This is a weight 10 observable, and you can once again repeat the same experiment. And now look at, for this weight 10 observable, the light cone gets a little broader, but we still have access to what the exact evolution should have been. Even here, the experiment agrees with what the right answer is. We're able to produce reliable results from the experiment, and then these classical approximations, they seem to completely fail, particularly as you approach pi over 2. Okay, I'd made a remark. One thing about the validity of our noise model, is it sufficiently representative? One very interesting thing to point out here is if you had access to the noise model, because the circuit is Clifford at pi over 2, you can estimate what the noisy expectation value should have been. We can do that, and we see very good agreement with the experimental data. So that tells us that it's sufficiently representative, but it also is giving you a very key insight that you can a priori predict for certain classes of circuits how much signal you might get from the quantum experiment. And that is very valuable to then get a sense of, okay, with this kind of signal, can I post-process enough to get what the ideal results should have been, right? We make things even more complex, now go to a weight 17 observable. That light cone expands even further. Here as well, it's not quite just brute force, but with additional tricks, we can have access to what the ideal evolution should have been. Once again, the experiment works reliably, and the MPS, the matrix product states, really struggle to capture this at this quantum dimension. Okay, so basically what we're seeing here is with an existing noisy quantum computer, we're able to produce accurate expectation values and regimes beyond brute force computation, and where leading classical approximations struggle. Okay. This, we're arguing, is evidence for the utility of quantum computing before fault tolerance, right? That we're taking a noisy quantum circuit, a short depth quantum circuit at this very large scale, and for the first time, we're producing accurate expectation values from this. This is the core primitive of almost anything we want to do in the near term, the vast majority of near-term quantum algorithms. Okay, that's where the evidence for utility is coming. It's not coming from the fact that we ran an icing model. It's not coming from the fact that we outperformed the considered methods. It's really coming from the fact that this is the core building block for what we want to do in the near term with quantum computing, and almost the prerequisite for any of this is you want to still produce accurate results, even if you restrict yourself to a short depth circuit. And that's something we're able to do now. Okay, and now the icing on the cake, puns intended, going beyond this regime of exact verification, is you can just make the observable a little more complicated, and now you don't have access to what the brute force estimate is, at least with the methods we tried. We don't have access to the exact curves anymore. But once again, at this pi over 2 point, this observable is once again a stabilizer. By Clifford simulation, we can verify it. The experiment performs well. The MPS completely fails, and then so we have reason to have more confidence in the exact in the experiment. In this case, then we go out to even longer depth, to a depth of 60, and look at the single site magnetization. Now the light cone basically covers up the entire device, all 127 qubits. Here at the start, you see some agreement. Things diverge at larger angles, and it remains to be seen which one is more accurate, and we'd love to know if the quantum experiment was performing correctly or not, right? This isn't even a comparison, but I know that there'll be curiosity about what were the kind of run times. A comparison is even meaningless because we're not comparing two things at the same level of accuracy, but the estimation of every single point run on a classical supercomputer, these were run on Lawrence Berkeley National Labs and Purdue's computers, were about 30 hours. If we compare that to the amount of time we ran on the quantum processor, that was just about 5 minutes of device averaging time, but it does take a lot more time to actually load the pulses and generate the circuits and compile and all of that. And so the actual wall clock time for the experiment is much longer. But that said, there are very, very trivial, immediately accessible speed improvements that are impending for us, right? So the elephant in the room, perhaps, is, well, is this quantum advantage, right? We don't know yet, really, and that wasn't even what we were trying to do, to be honest, right? We didn't choose a circuit, with a formal hardness result. The first step really is you first want to test reliability at the scale. This has not been done in the past, that you can run a circuit at this volume and get accurate results even from a noisy device, right? That said, we're already seeing that these experiments are motivating extensions to state-of-the-art classical methods. With our collaborators as well, there are obvious things to try next. And there will be a continuous back and forth. This is not something that one can do in a single paper. This will be a continuous back and forth between classical and quantum. We absolutely expect the classical methods to evolve and do better. But there's also a lot of reason for optimism, right? On the quantum end of things. If you look at the kind of coherence times and the error rates that we have on the device, which is the state of the art, at the scale, for this Eagle R3 device, and compare it to the kind of metrics that we have even within IBM for the best numbers, there's an order of magnitude improvement in coherence time, in gate fidelities that's really impending. And all of these coming in is going to feed into the kind of circuit volumes that we can do, the number of qubits, the number of gates in the circuit. All of this is going to make it increasingly harder in the days to come. Okay, so with that, I'm sorry that I went a little over time, but these are my take-home messages. I won't repeat the first couple, but yes, I think what we now really view this as, it's really a scientific tool for the exploration of quantum applications at non-trivial scales. For testing out all these near-term quantum algorithms that we had, but just couldn't test at the scale. The essence here is to first build trust in the device and the methods. We can now begin to choose, very much, circuits with formal hardness proofs, and that's something we'd love to know. What's the thing to run next if people have ideas. There are even more powerful error mitigation methods in the oven. I didn't get a chance to talk about them. They call probabilistic error cancellation. And all of this, these improvements in the scale, quality, speed will all add to what we can do with error mitigation and the kind of circuits that we can run in the days to come. Okay, with that, thanks very much for your attention. Happy to take any more questions.
Okay, so thank you, Dr. Kandala, for this beautiful talk. So the floor is now open for question. So question from participants.
One question from my side.
Yeah, please.
Thanks for the nice talk, Abhinav. So I would like to ask, how close is your work to being an industry use case?
Yeah, that's a very good question. so the I'd say it's an enabler for that. Okay, so I really view this as now a tool that hopefully folks from industry, from academia, can think of as something to do calculations that they would otherwise want to do on a supercomputer, right? On a classical supercomputer. That's something to explore at this point. You could think of applications in machine learning, kernel estimation algorithms. You could think of other quantum simulation experiments, any of these, but all of these eventually just tie down to running a short depth quantum circuit and measuring an expectation value. That's what we're trying to do in the near term, largely, right? And for that, so basically, this work in itself is not trying to probe one particular application, but I look at this as the enabling tool for the exploration of those applications. Right?
So it's basically on the exploratory level at this moment.
I'll say it's providing a capability.
Okay.
It's providing a capability. That's what this is, right? I mean, it's like the way you want a supercomputer to run some calculations accurately for you. Now you have perhaps a quantum supercomputer to try and run the same calculations for you, perhaps better. What those calculations are for, that really is a different question. That's not something I'm addressing at all yet. But all I'm saying is that for the exploration of those applications, in the near term, the core building block is always the same. And this is the tool that enables that.
Okay. Yeah, fair enough.
Okay, any other question?
Yeah, I have one question. No, no, no.
Yes, sir.
Yeah, Dr. Kandala, I belong to ISO Kolkata, so I do appreciate your feelings which you expressed. We are all familiar with Professor Chari. He visited ISO Kolkata when he just came to Berhampur, and in fact, we are going to have a special colloquium from Professor Anil Kumar IISc in this platform in honoring Professor Chari's contribution. I would just like to ask a very simple question. This transverse field ID model phase transition, was it able to be reproduced through this IBM platform?
Right. So here we're not looking at ground state properties of the transverse field icing model. We're looking at dynamics. So this is looking at the quench evolution. So that's not something we were even probing at this point, right? We were just looking at the quench response to certain parameters.
But even looking at the correlation function, wouldn't that show some behavior like near the phase transition, the behavior of the correlation function would indicate phase transition?
No, it could. I think that's something we could certainly measure and probe. It's not something we actively did in this experiment, because I think for us the focus was on, is there even something you can do accurately or reliably, and that was. But thank you also for your kind words.
Thank you for a very nice stuff.
Okay, Ranjit, go ahead.
Yes, thank you for your talk. I have few questions. So first one is, one interpretation you have provided that fidelity does not reflect complete information about the state. So my question is, what kind of other interpretations one can provide to justify that other criteria, for example, correlation is better than fidelity?
Yeah, so I think that the more precise statement maybe is like to think of fidelity as the worst case metric. Okay, that's perhaps how I would phrase it. And like in that simple example that I walked through, right? You can see that even for just asking the question, what's the global magnetization like, you can have access to something that's a lot more accurate than how much your fidelity is suggesting. So how does one know a priori what quantity has enough signal or not? That's tricky. I think you can always work with special cases or certain circuit families where you can have access to classical simulation. So this is, for instance, in these Clifford parameters, and that's why I was motivating precisely this point here at the pi/2. When the circuit is Clifford, once you have access to that noise model, you can make an estimation of how much signal you might have, even if you can do a rough fidelity estimation, but also you can get some sense of, hey, this was the noise model, this is the circuit, what would the signal be for this kind of correlator, and then have some estimation and get a feel for it. But yeah, it's not something you can. Yeah, it's not something that's necessarily analytical that I have in general, but yeah, I think there's a way to build some feel for the kind of signals one might have.
Thank you. Do you see impact on the performance of algorithms, quantum, if state is maximally entangled or not? And another question related to this, do you measure entanglement, whether state is maximally entangled or not?
So we're not measuring if the state is maximally entangled or not, but one effect of increasing entanglement in the circuit actually comes through in the tensor network methods and how they fail, right? As like I was referring to how these seem to work quite well at low angles, but then they begin to break down at larger angles. The idea there is you're building correlations across the device that this tensor contraction is not able to accurately represent anymore. So as we're going from 0 to pi/2, we are building more entangled states with longer correlations. That's definitely happening. What was the first question? I think I've forgotten that, if you don't mind repeating.
Yes, I will repeat. Do you see impact on the performance of algorithms if state is maximally entangled or not?
Yeah, absolutely. So I mean, you can. So depending on the details of the circuit, it all connects to how quickly errors can propagate and things like that. So yes, as you make things more entangling, how errors spread in this light cone, all of that connects. And yes, like this certainly can impact the performance of things like expectation value estimation. But this is exactly why even in those non-trivial regimes, we want to build tools and capabilities that give you access to accurate estimations.
Thank you. Last question. In your circuit slide, why resonators have got zigzag shape but not straight line? Moreover, you are injecting monochromatic waves.
Yeah. So that's more of a real estate issue. So the length of the resonator dictates the frequency of the resonator, and you only have a limited amount of real estate on your chip, and so you want to package them in a small area as possible, and that's why you have that kind of zigzag. But that's the very trivial reason for why.
It means to select certain modes which you need for the interaction.
Yeah.
Thank you.
Okay, so we are running out of time. So maybe last question. Is there any other question?
Hi, Dr. Kandala. I would like to ask a question. So, since you are using to amplify the noise, the probabilistic error amplification, why are you not using the Hamiltonian scaling to increase the noise? Is that not precise enough?
You mean the pulse stretching?
Yes.
Yeah, exactly. So there are assumptions you're making there, about the time invariance of the noise, and this is actually one reason why we were able to, why zero noise extrapolation was very popular to begin with, because people were just making assumptions about the nature of the noise, and then doing what was most accessible to them to amplify it in some way. But then you begin to see the impact of that on the quality of the extrapolations. When you begin to do extrapolations, you'll see very often that some of them just go completely unphysical and things like that. I think a lot of that got a lot better behaved once we spent the time and effort to characterize the noise more accurately and then manipulate it in a more controllable way.
Okay, so if I recall correctly, your past works with error mitigation, you have used the pulse stretching, right? So the result should be better if you go back to it using probabilistic error amplification, is what you mean?
We haven't explicitly done that, but I have reason to believe yes. Right? I mean, even at this experiment, at some point we were working with the pulse stretching. The pulse stretching also comes with a large calibration overhead, because you have to recalibrate the gates for every pulse for every pulse stretch, and doing that for 127 qubits. It's possible, but it's very time consuming, right? Things were much more efficient in the sense that once we calibrated the gates once, we don't need to touch them again for this approach. So that was another nice feature of this direction. Yeah, thanks for that.
Yeah. So another linking to your previous work. So now, since we can do such a thing, error mitigation on a 127 qubit device, so could we now link it to huge number of large atomic molecules, like something like a drug or something? Do you think we'll be able to do something with those now?
So, so the idea is it's not just number of qubits. I mean, you can certainly map to larger Hamiltonians, but then the question is also, are those circuits still going to be short depth, right? And that has to be explored. Can you map those problems also, on a sufficiently short depth circuit, and how short that depth will be? I mean, here we went up to depth 60 with improvements in coherence and gate fidelities. Those will get larger, but that's one motivation for this 100 by 100 thing. That it's useful to ask what applications can one fit into 100 qubits depth 100, because that's something we think we can get to in the next 1 year, and that would be the way to think about what applications fit in the near term.
Thanks a lot. Thank you for your talk.
Okay, so thank you very much, Dr.
Just one question.
Yeah.
Can you shed some light on what is the fidelity of the entangling gate that you have used?
Yeah, it's about on the median is a little less than 1%. So Eagle R3, so that's the 1%. It's about 0.8% median gate fidelities.
Okay.
But I'll just quickly say that also we're not optimizing for gate fidelity in our calibration scheme. We're optimizing for the layer because all of these are parallelized.
Yes.
Once we identify the slowest gate, all the gates are slowed down to the same speed. So in principle, if you looked at like the individual gates, they could have been optimized even better, but that's not something we're concerned with in this implementation.
Okay, just last question. So like in superconducting circuits, we also use the resonators, and this is a complete digitization of the problem Hamiltonian into the qubit subspaces. But have you ever thought of like using the resonators in order with the qubits to design like a hybrid qubit bosonic architecture to simulate like a larger class of systems like electron-proton interactions?
I think it cut out for me, but I think the question, if I remember, if I can piece it back, is have I considered using resonators as part of the computation?
In IBM Quantum, have people thought about using such hybrid designs?
Yeah, not to the extent. I know this is like an active area of work, like even in the context of trying to do error correction. It's something many groups try and explore. It's not something that I have actively thought about as much, but yeah, we always have a keen eye on what's going on in academia as well, and seeing if there's reason to pivot, we will.
Yeah. Okay. Thanks.
So great discussion. So on the behalf of QIQT team as well as from my personal behalf, I am thankful to Dr. Kandala for giving his valuable time. So thank you very much. We will see you in
My
next
pleasure.
QIQT also. Okay. Thank you. Thank you very much.
Thank you. Thank you so much. Yeah.
Okay, so
yeah. I think is that the last talk today, or there is something more?
Yeah, I think this is last part.
This concludes the day, sir.
Yeah. Okay, so we will meet tomorrow in the morning session around 10.
Yeah.
Okay. Thank you very much.
Thank you. Good night. Good night, Dr. Kandala.
Good night.
Good morning.
Bye.